Hello everyone. The session is talking about industrial waste management too. I invite Professor Dr. Tijen Enel Bektaş. Hello, Tijen Hanım. Can you hear me? You are close your microphone. Can you open it?
Sorry.
Yeah, it's okay. Thank you.
Okay, dear participants and presenters, welcome to the 5th Eurasia Waste Management Symposium. The topic of this session is industrial waste management. I'm here as the chair of this session. I'm Professor Dr. Tijen Enel Bektaş. I'm working in Chemical Engineering Department at Çanakkale 18 Mart University. There will be 7 presentations in this session. Each presentation has a total 15 minutes. If you do 10 minutes presentation and 5 minutes question answer, I think I will be efficient. In order not to delay the session duration, I ask the presenters to abide by this time. I want to start the session now. The first presentation will be made by Rupner Martins. Is the presenter here?
Hello, good afternoon, everyone. My name is André. I'm a professor from Brazil, and I sent this presentation for the Congress. Could you check, please?
You are not Martins?
No, he is the student. I'm his professor.
Okay, I will share.
Yeah, okay.
Rosa.
Probably the Congress received the presentation.
Okay, if you introduce yourself, we are pleased, and you can start your presentation. We are listening to you.
I sent the presentation because previously in another section, I had problems with my video to share the presentation. So I entered in contact with Noyan from the Congress, and I sent him the presentation, the file. And he told me that he received the presentation and will send the presentation for the chair. But I can try to open here, but I don't know if the sound will.
I tried to open. Just a second.
Do you have the file? Okay, yes, this one.
Welcome. My name is Rubner Marques, and this is a presentation for the paper entitled Adsorption of Dye from Wastewater Effluents from Textile Industries Using Alternative. Our objective was to evaluate the adsorptive capacity of alternative materials, which when employed in a large scale could bring substantial contributions in terms of waste valorization, zero waste strategies, and agricultural.
Excuse me, the presentation stops.
Agricultural waste management.
Okay.
The objectives of this paper were to evaluate the adsorptive capability of Chitosan and Sawdust for removal of the textile dye acid yellow 25 from aqueous medium, to determine the balance times, kinetic behavior, and the adsorption isotherms for both adsorbents, and to determine the influence of pH values on the adsorbent capabilities for both adsorbents. The first step was to determine the balance times for both adsorbents, which was made via kinetic tests. The data obtained in this experiment also showed the removal percentage for each adsorbent and enabled the construction of the kinetic curves for the adsorbents, which followed the pseudo-second-order model. In possession of the balance times, the next step was to construct the adsorption isotherms using the Langmuir and Freundlich isotherm models. The kinetic tests were made as follows. 12 systems with identical absorbent masses and initial dye concentrations were prepared in Eppendorf tubes. These systems are subjected to stirring, beginning simultaneously, and the systems are removed from stirring one by one in predetermined time intervals. The remaining dye concentration is measured via spectrophotometry. The adsorption isotherms were built as follows. 15 systems with roughly equal adsorbent masses and different initial dye concentrations are prepared in Eppendorf tubes. These systems are subjected to stirring until the balance time is elapsed. The experiment was executed in pH values of 7 and 4. The experimental data and the results were synthesized in 8 graphics, which are removal percentages for each adsorbent, the kinetic curve for each adsorbent, Langmuir isotherms for each adsorbent in pH value of 7, and Freundlich isotherm for each adsorbent in pH value of 4. Here we see 2 graphs, which are the comparative removal percentages for Chitosan and Sawdust, in which Chitosan is shown in blue. These results led to the conclusion that the removal percentage for Chitosan is 84.69%, while the Sawdust removal percentage reached 53.32%. As was described before, this experiment also shows us the balance time for each adsorbent. Chitosan's balance time was shown to be less than 1 hour, while Sawdust balance time was of 72 hours. On to the absorption kinetics. Here we can see the linear curve for Chitosan adsorption kinetics, which follow the equation shown. In an initial concentration of 50 milligrams per liter, the Chitosan adsorptive capability was of 8.0841 milligrams of dye per gram of adsorbent. And the constant for pseudo-second order adsorption rate was of 0.3464. Regarding Sawdust, the same linear curve was constructed based on the same equation. For an initial concentration also of 50 milligrams per liter, the Sawdust adsorptive capability was of 5.4529 milligrams of dye per gram of adsorbent, while its constant for pseudo-second order adsorption rate was of 0.0291, which shows that in relation to Chitosan, Sawdust has a lower adsorptive capability and also a much lower adsorption rate. Moving on to the adsorption isotherms. First, we have the Freundlich isotherm for Chitosan in pH value of 7. The curve was built on a nonlinear regression which follows the equation shown. For Chitosan in pH 7, the Freundlich constant was 5.8267, while the exponent 1 over n, which represents the adsorbent's heterogeneity, was shown to be 1.61. The Freundlich isotherm for Sawdust in pH 7, which was constructed following the same equation, shown the Freundlich equation to be 0.3788, while the exponent 1 over n was shown to be 1.2997. In comparison, we can see that the Freundlich constant, which determines the rate of adsorption, is shown to be much higher for Chitosan than from sawdust in same value of pH. The Freundlich equation in pH value of 4 shows the Freundlich constant to be 30.4768 and the exponent 1 over n to be 1.6499. While the exponent did not show significant change, the Freundlich constant had a major increase, indicating that the decrease of pH favors the adsorption rate for Chitosan. For sawdust, the Freundlich equation in pH value of 4 shows the Freundlich constant to be 0.5736 and the exponent 1 over n to be 1.3077. Once again, the exponent did not show significant change, and while the Freundlich constant did increase with the decrease of pH, it still pales in comparison to the values shown by Chitosan in the same conditions. The Langmuir adsorption isotherms were also built on nonlinear regressions, however following a different equation as shown. For Chitosan in pH value of 7, the maximum adsorptive capability was shown to be 31.5570 milligrams per gram, and the balance constant, which also denotes the rate between desorption and adsorption rates, was shown to be 2.8420. For sawdust, the Langmuir isotherm shows that the maximum adsorptive capacity is of 25.7943, while the balance constant is 109.4880. This indicates that the rate between desorption and adsorption rates for sawdust is very high in a pH value of 7. In pH 4, the Langmuir isotherm for Chitosan shows an adsorptive capacity of 56.5327 milligrams per gram and a balance constant of 0.9047. Being lower than 1, these constant values show that the adsorption rate is higher than the desorption rate, indicating an advantage in the decrease of pH for Chitosan. Sawdust in pH 4 shows an adsorptive capacity of 43.3122 milligrams per gram and a balance constant of 136.3937. Although the adsorptive capacity increases with the decrease of pH, the desorption-adsorption rate
Hello, we will continue. Dr. Tijan.
Okay, is there a problem?
Hello, what happened with the presentation? Because I sent a presentation for
Presentation is repetition again. Is most problem.
Can you tell?
I don't know what happened because I just sent the file. It's impossible to play the presentation again in the where it stops. Please.
And conclusion. Tell us conclusion.
Just a minute. because I'm representing Martins because he had an unfreezing event. Just a minute, I'm opening the presentation to read the conclusions.
Okay.
In pH 4, the Langmuir isotherm for Chitosan shows an adsorptive capacity of 56.5327 milligrams per gram and a balance constant of 0.9047. Being lower than 1, these constant values show that the adsorption rate is higher than the desorption rate, indicating an advantage in Sawdust in pH 4 shows an adsorptive capacity of 43.3122 milligrams per gram and a balance constant of 136.3937. Although the adsorptive capacity increases with the decrease of pH, the desorption-adsorption rate increases even further, showing that the desorption rate gets higher with the decrease of pH for sawdust. Our conclusions with this paper are: the Langmuir isotherm model better describes the adsorption mechanism for both adsorbents, as shown by the coefficients of determination below each graphic. The parameters for the Langmuir isotherm involving Chitosan show that both its adsorption capacity as well as the rate between adsorption and desorption velocities increase as pH decreases. The balance time for adsorption in Chitosan was shown to be low, and its adsorbate removal capacity is high. The results indicate that adsorption processes using Chitosan can be a promising alternative to replace conventional adsorbents in removing textile dyes from aqueous medium. The reduction in pH value increased sawdust adsorption capacity, but also reduced its rate between adsorptive and desorptive velocities. The balance time was shown to be high, and its adsorbate removal capacity is moderate at best. The results indicate that adsorption processes using sawdust in aqueous medium are not viable, especially in an industrial scale. Well, this marks the end of this presentation. Your time, attention, and patience were very much appreciated. Thank you, and have a nice symposium.
Okay, thank you.
Thank you.
Are you going to answer the question?
If you have some questions, I have the Rubner contact. I'm sorry, but I'm not able to answer specific questions. I'm only representing in the symposium with this article.
Okay. Is there a simple question? Can I ask a question to you? The Wastewater, is the real Wastewater real textile factory?
The sawdust?
No, Wastewater.
Can you repeat, please?
You use Wastewater effluents. Okay.
Can you write, please, West?
Is the real textile Wastewater or synthetic? You can use you can do synthetic Wastewater or real Wastewater. Which one?
I didn't understand your question.
Okay. Okay. I want to.
Okay, thank you.
Thank you. I want to go to next presentation.
Okay, thank you.
Professor Dr. İnan Özçimen is the presenter here.
Actually, I'm going to present Professor Bektaş.
Okay. Özçimen, I want to introduce the presenter briefly. Professor Özçimen works at Yıldız Teknik University, Bioenergy Department. Özçimen was graduated from Istanbul Technical University in 1998. She finished PhD study on the biomass energy technologies in Istanbul Technical University at Chemical Engineering Department. She is interested in the renewable energy source, thermal conversion technologies, energy and environment, microalgae biotechnological application, and renewable biomaterials. Okay. You can start the presentation.
Okay, just a second. Okay, can you see?
Yes, I can see.
Okay, I'm going to start then. Thank you. Hello, I'm İnan from Yıldız Technical University of Department of Bioengineering. I'm going to present our study on production of iron oxide nanoparticles from Ulva Lactuca with green synthesis for use in dye adsorption. As you know, water pollution is one of the most important problems society is facing today. Recent environmental problems and the development of the industry have led to a gradual decline in the amount of potable water. Especially, the synthetic dyes used in the industry cause serious water pollution. Synthetic dyes are man-made, made from petroleum, sometimes in combination with mineral-derived components. They are used in many application areas like textile, leather tanning, paper production, photography, rubber, plastics, cosmetics, pharmaceutical, and food industries. However, there are some problems using these synthetic dyes. For example, up to 15% of the used materials are discharged into the wastewater stream. And they are not easily biodegradable. They may include cancer-causing agents. They can threaten to aquatic life and mankind indirectly. They may be toxic and they can cause allergic dermatitis, skin irritation, and they may have mutagenic and carcinogenic features. In order to prevent the environmental damage of these dyes, wastewaters are treated using many methods such as adsorption, chemical coagulation, precipitation, ultrafiltration, and ionizing radiation. However, adsorption comes to prominence due to its easy design and operation, and also its high efficiency. As adsorbent, many materials can be used, like nanoparticles, activated carbon, biomass, biochar, Chitosan, zeolite, and struvite. However, except from nanoparticles, these materials have low adsorption efficiency. On the other hand, nanoparticles have large surface area with small sizes in nanoscale, and they have high reactivity. Among these nanoparticles, metal oxide nanoparticles can exhibit unique physical and chemical properties with their limited size and high surface area. And these properties vary according to the synthesis and processing method. Many methods can be used to produce metal oxide nanoparticles, like solution-based, steam-based, and biological. Green synthesis is a biological method which has advancement over chemical and physical method, as it is cost-effective and eco-friendly. It is simple and economical. It doesn't require the use of toxic substances. It is suitable for a wide range of commercial production. Various natural sources can be used for the production of metallic nanoparticles, like plant, bacteria, fungus, yeast, and algae. In this study, we focused to produce metal oxide nanoparticle to use in the dye adsorption. So we produced iron oxide nanoparticles using Ulva Lactuca macroalgae via green synthesis to remove Ramazol brilliant blue R dye. In this study, the nanoparticles by FTIR, DLS, and SEM. Also, in the batch adsorption experiments, adsorption capacity, adsorption kinetics, and adsorption isotherms were determined. In the experimental study, we used Ulva Lactuca as a raw material, which are collected from coastal areas of Marmara Sea. They are considered as waste, so that's why we choose this material. Microalgae firstly washed with distilled water to remove the impurities, and after that they were dried at 70 degrees Celsius for a night and then powdered. After this, algae were extracted and filtered, and the extract were mixed with metal solution. In this study, we use ferric chloride. After mixing, we obtained a dark solution. This is one of the proof of the chemical conversion of producing iron oxide nanoparticle. As I said before, we characterize these nanoparticles with their sizes, with zetasizer device, and we also use FTIR and SEM. For the adsorption experiments, we used Ramazov brilliant blue R dye, which is one of the most important reactive dyes in the textile industry. It's an anthracene derivative and represents an important class of toxic and recalcitrant organopollutants. Iron oxide nanoparticles were used to remove Ramazov brilliant blue R dye from aqueous solution. Firstly, 1000 mg per liter stock solution of dye was prepared, and this stock solution was diluted to standard concentrations of 20 to 100 mg per liter. The pH values of the standard solutions were adjusted to 3, in all cases with using hydrochloride or sodium hydroxide solutions. In the batch adsorption experiments, 20 mg adsorbent was thoroughly mixed with 10 ml aqueous solution of dye in a sealed conical centrifuge tube placed into a tube rack. These experiments were carried out at a constant agitation speed of 200 rpm and a temperature of 25 degrees Celsius for 60 minutes. After each experiment was completed, residual concentration of dye was determined by spectrophotometrically. The amount of the remaining dye was determined from the calibration curve. The adsorbed quantity was calculated using the following equation, and kinetic data were fit by employing the pseudo first order and the pseudo second order models. Also, the adsorption process was analyzed by using Langmuir and Freundlich isotherms. So let's see the results. Firstly, we characterize our raw material, Ulva Lactuca. Ulva Lactuca's chemical content is a little bit different from the in comparison with the literature, but this is expected due to the seasonal changes and the location site. After that, we characterize the iron oxide nanoparticles. Our nanoparticles has very small sizes. Its average diameter was 40 nanometers, and as you can see the figure, there are two peaks. This shows us there is an agglomeration, and also in the same image, you can see the nanoparticles are spherical and in an agglomerated state. Also, with using FTIR, we see the iron oxide peaks in the FTIR spectrum. For the adsorption experiments, adsorption capacity increased with increasing dye concentration. The adsorption rate was very fast at the beginning at the process, then it decreased until the equilibrium is reached. The optimum contact time required for the equilibrium was found as 60 minutes for iron oxide nanoparticle. The maximum adsorption capacity was found as 22 mg per gram for initial dye concentration of 100 mg per liter. On the other hand, the minimum adsorption capacity was found as 4 mg per gram for initial dye concentration of 10 mg per liter. Also, we calculated the adsorption kinetics. As I said before, two kinetic models were tested to explain the adsorption kinetics, and the rate constants were calculated. It was found that the pseudo second order is in good agreement with the experimental data, and correlation coefficient is higher than the pseudo first order. Also, to understand the adsorption process, this process was analyzed with Langmuir and Freundly isotherms, and best correlation was obtained with Langmuir isotherm. In summary, we produced iron oxide nanoparticle with 40 nanometers, and the dye adsorption capacities of these nanoparticles were between 4 to 22 milligram per gram. In conclusion, the iron oxide nanoparticles produced via green synthesis from Ulva Lactuca can be used for removal of dye from aqueous solution. Thank you for listening.
Okay, thank you for your presentation. Is there a question? Any question?
Can I ask something?
Yes.
Sure.
Thank you very much for your presentation. I have a question about the legal limitation for the dye concentration. Is there any limitation for the dye concentration?
I couldn't understand the last part.
Excuse me. Is there any dye concentration for the legal limitation?
I'm not sure actually, but for legal usage.
For legal usage, not for legal usage, you can use those nanoparticles for removing some dye components from the water. Is it suitable for the legal limitations? I ask something.
Yes, sure.
Thanks a lot.
I want to ask one question. Why didn't you examine the effects of the other pH? Why only pH 3?
Very good question. This is an ongoing study. This is Anıl Tevfik Koçer's PhD study. So we present here the small section of this study. Of course, we are examining the other pH levels. I could say that increasing pH levels, lowering the adsorption capacity, but we didn't present it here.
Why?
Why? Because it was raw data. We should repeat our experiments. I hope so. You will see that in our article.
Thank you.
You're welcome.
Yes. The next presentation, presenter Zöhre Kurt.
Yes, I'm here.
Okay. Zöhre Kurt is a member of Environmental Engineering Department at Middle East Technical University, and her research focused on environmental process that supports sustainable treatment. Over the years, she worked in various aspects of biochemical process in environments that lead her to publish in high-impact journals, one of which is Nature Biochemistry. In the last 2 years, while working in Middle East Technical University, she has developed sustainable projects, and she was awarded with L'Oreal National Young Woman in Science Award and Science Academy's Young Scientist Award Program. Very well. Congratulations.
Thank you.
You can start your presentation.
My presentation is going to be one of the very small projects that me and my team worked on over the years. It is called Estimating the Adsorption Capacity of Mining Waste, to sum up Leonardite, for treatment. And in this case, we checked the treatment capacity of copper. So I want to start my talk with just explaining why it was important. So throughout the years, we can observe that the change in cropland area in the world. So what you see here is anything that is in orange and red is decrease of land that is available for agriculture. And anything in green is an increased levels of agriculture land throughout the entire globe. What we have observed, and of course everybody else in the world observed, is that there was a huge decrease in the land use for cultivation, which also created a problem with production of food that is necessary for eating, and also it brought a dilemma of using some food materials for biodiesel and fuel purposes. However, it was very important to understand what actually is causing this problem in the environment. And there are many studies that have been done already, and I'm going to present this little figure that is explaining major sources of decrease of land and industrial contamination. We see that throughout the years, there could be some natural effects, natural causes like volcanic eruptions or wind-blown dust particles or sea sprays or aerosols that could cause a decrease of land in agriculture. But also there are basically the rest of the reasons are human-made. One is agricultural reasons, which is inorganic fertilizer usage, pesticides, and sometimes fly ash could cause decrease of land, wastewater if it's not used correctly, and fungicides, as well as industrial components or domestic components like wastes, some ore and minings, of course, land that has been taken for domestication and building houses and apartments instead of being used as agricultural lands, and other things that are like open dumps or roads that have been built are reasons for decrease of agricultural land, hence also causes reduced crop production. And one of the biggest reasons of also reduced crop production is not only the amount of land that has been decreased, but also the fertility of the land that is present. And the fertility of the soil is related with how much microbial activity is present in the soil, how much minerals are present, and whether or not there are contaminations in the soil. And of course, you know, we as a scientist and also many people have been trying to find different ways in order to regain the use of those soils and be able to provide a better and useful agricultural soil. So one thing that we have observed, and this is a project that has been carried on in Panama, is Leonardite. You might have heard it in Turkey too. Leonardite is a mining waste. It used to be a mining waste. If you see from the figure here, you will see that right before, you know, like reaching some, whenever there is a formation of coal and lignite, before you are actually reaching the lignite, you are producing Leonardite. It's an oxidation process. And Leonardite is something that was not wanted in the mining wastes. And people were used to just dump it with the soil back in the day. However, agricultural usage of this component has been discovered, and right now many places in the world are using Leonardite. And interesting enough, the main suppliers of Leonardite are Turkish companies, which are located mainly in Çanakkale, that are producing this unwanted chemical that right now is a margin of profit. So why is it so important? It's because mainly it contains humic particles, and humic particles are supporting the growth of plants. However, even though agriculturists are able to observe an increase of yield up to 200%, nobody really, like up to this point, started studying extensively the reasons why Leonardite was so important and was so helpful in the soil. What you see here is application rates, so it varies a lot. Sometimes you can see that 10 grams per kilogram of soil of Leonardite has been applied in some places in the world. This is not only Turkey, and the pH conditions also varies, and these variation of pH conditions depends on the soil that was chose to for application of Leonardite. And here is what I actually have explained a minute ago. What happens is you have humic acids and amino acids in the environment. There is a qualification that creates lignite, and oxidation of lignite actually creates Leonardite. And if you want to extract the humic acids that really support the growth, there is a potassium hydroxide extraction methodologies that is used by some companies before they sell their product. But most of the time, what you would find is Leonardite in raw form, which is whatever is shown in this picture right here. How does Leonardite help? It stimulates growth process of plants, strengthens the immunity system of plants. It stimulates germinations of the plant, and it's helpful for the root growth. Hence, the application of it is really right before plantation and during the growth of the plants. And then it accelerates the periods of plant ripening. I was not allowed to show all the yield data from the agricultures that I work with abroad, but I can tell you in confidence that, for example, in Panama with agricultures that we have been working, we see like even more than 200% of yield increase whenever Leonardite is applied as 5 grams per kilogram of soil in most of the places. One of the biggest problems that we see in the world, in the agricultural places, is the irrigation water. So I've been telling you that Leonardite is fantastic. It works good. Now the question is, what does it do and why it works so well? And one of the reduction of the crop yields, like I told you before, was the contamination in the environment and also contamination of the irrigational water. What we see in the fields is usually that the well is opened in the agricultural field, and then this well is used for irrigation of the plants, and that water may or may not be contaminated. So in several places that we have been called to detect the soil properties, we observed that actually the water that is used for irrigation from the wells is also contaminated. And it's contaminated either with pesticides, with heavy metals, with nitrites, sometimes with ammonia. And when it's applied back to the plants, because of sometimes high concentrations of things that are present, the yield is actually decreased. Observing this behavior of the agriculturists made my team to start exploring the idea of pump and reuse. In this case, it was pump and fertilize. We have published one paper, submitted a couple of more. And what we are really trying to explore is how we can actually use this contaminated water and what can we do in the field in order to be able to utilize this contaminated water to create a sustainable solution for water reuse without really doing further treatment processes, because as many of you know, pump and treat is something very expensive. Even bioremediation has some time delays, and if we actually could use these things that we call contamination for our advantage as goodies, then we thought that might be a better solution, and that's what we're exploring here. In our laboratories, we have columns, and here is what you see here are our columns that have soil. In this case, what we have done is we have applied Leonardite to an area of the column that represents the topsoil, because that's where exactly Leonardite is applied in real life. And then we decided to pass contaminated water and observe what is going to happen, as well as we analyze Leonardite on its own about its adsorption capacity. In this case, our first goal was to determine what will happen with copper, because copper was one of the contaminants that have been observed in the areas that we went sampling for soil. So our question was, can copper contamination be prevented mainly with Leonardite, and if Leonardite could actually work? What we have done is, like you see here, we have different soil texture properties and sorption properties of many different soils. Even though we have collected soil samples in many places, we also wanted to model our findings based on generic data that have been created with different types of soil. And here you see different parameters of soil that has been mainly used in the agriculture throughout the globe. They have different names and they have different clay, silt, and sand properties. You see their capacity of adsorption, and this is related with copper in this case, because that's what we're interested in. And then we see the KF values and OC values as well. And what we have done in our modeling aspect is we used Creewer 3.0, which is a program that you can get all the data that is related to crop growth. So whenever you have a crop that is planted in a field, in this case, we have chosen corn, maize, because that was one of the plants that have been used rigorously everywhere. You take the need of the plant, of how much water the plant will need, and Creewer provides you with that information, as well as the meteorological information of more or less how the climate in specific areas where you see the soil components can be changed. And you see the equation that they use here for plant growth. And here is the data that we have collected about irrigation, how much the crop needs and crop coefficient needs and all. Then we plugged everything in Hydrus one-dimensional model for us to be able to see what is really going on in the soil, because the main aim was actually to understand if the Leonardite was helping the soil conditioning and if it was actually preventing the contamination. On the lab, on the site, we have measured the maximum absorption capacities of Leonardite. When we speak about Leonardite, remember I told you that Leonardite can be obtained from different types of mines. Hence, the humic acids, the fulvic acids, and all other properties of Leonardites can change from type to type. So every single time, whenever you have a Leonardite, it's recommended for you to measure. We have analyzed our Leonardite. We send it to be analyzed in a laboratory. And here you see the properties. And then we determined the maximum absorption capacities of Leonardite in different temperatures for the solubility levels of copper. We use this information to plug everything in Hydrus model in order to be able to determine if this logic will be able to be used really in globe. What we saw here is, I'm going to show you the main 4 different soil analysis and the data that we observed from here. What you see here is how much copper it would have leached based on the water that has been provided in nanograms. and I will give you values that will represent how much of copper will be saved by Leonardite in red here. So with the first type of soil, what we see is if we apply Leonardite in topsoil with 5 grams per kilogram ratio, we can save up to 0.8 kilograms of copper contamination just because of the adsorption capacity and desorption properties of Leonardite. So it will be able to hold 0.8 kilograms of copper if it's mixed, if it has the soil underneath in with the properties that are provided here. The same thing will happen, will change to 2 kilograms of copper per hectare per year with a different type of soil. And we see 5, and it's going to go up to 10. So we have a range between 0.8 and 10 kilograms of copper per hectare per year that could be prevented from the contamination. What we have done now is, after being able to model this, we also use data from the laboratory to verify these tests. But one thing that was very important to know is what will happen throughout the years if we just lay down Leonardite in the fields. That will have told us if the soil properties really were getting better within the years. So what we did is we laid down this, in the model, we laid down Leonardite as the first 5 centimeters of the field. And then we started applying the climate data, meaning like rain will come and then all the irrigation will happen with contaminated copper water. And then what you see here is the 0 level is where your soil is. This flux is what you put in every single time. So this is when you do irrigation with the contaminated copper water. And what you see after 0 is what will leach down. And this is time of days. So you would see that for the first 123 days, you will not see any leaching. If you just add the copper water once, and if you just keep watering, the desorption will happen just in a very few amounts, throughout the years, which will really not cause that much of an effect. In the second figure, you see that we are watering the copper contaminated water for several times. And when you see is again, the decontamination will keep up to 2000 days. But after that, you will see that this is leaching. Why is this important? That means that once you lay down Leonardite in soil fields, if you have copper contamination in the area, definitely you need to change this Leonardite layer at least before 2000 days. And this is what it really, this study tells you. As conclusion, we were able to observe that in very high and very low permeable soils, there is a susceptible copper leach, that in soils with fulvisol, salty clay loam have very low leaching. The loamy sand copper use efficiency is the highest, and at the end we could say that application of Leonardite in the soil will actually really help to reduce the risk of heavy metals. In the future, of course, we need to observe those things in the fields, and whenever we are measuring the soil properties, one important parameter that is organic matter of the soil should be definitely determined. That's one thing that was lacking in the global databases. And also the erosion and runoff were the parameters that we were not able to observe and find. That's why we had a one-dimensional model that we tested our findings with. And in case there is erosion and runoff, of course, because we're going to be losing the first layer of the soil, all our findings would change. So that's a very important issue that we have to address. And then we have to determine the aquifer heterogeneities to be able to determine also 3D models, as well as having the erosion and runoff data. So here is our references, and this study completely was financed by the Panamanian government. with a project and some personal funding that the Panamanian government gave me. So I have to acknowledge that. And thank you for all of your attention, and I will be happy to answer any questions.
Okay, thank you very much. Is there a question? No question.
Okay.
Okay, if there is no question, I want to go to next presentation immediately. The next presentation will be made by Büşra Kara. Okay, Büşra Kara works on a TÜBİTAK project related with biological phosphorus recovery as a secular at Marmara University, Environmental Engineering Department. Okay, we are listening to you.
Thank you, Professor. Well, hello everyone. Can you hear me?
Yes, we can hear you.
Okay. Hello everyone. Yes, I'm Büşra, and currently I'm a master's student studying in Environmental Engineering Department in Marmara University. Today I'm going to be presenting you with our recent study that covers adsorption of ammonium and phosphate ions with a focus on their adsorption performances on bare and composite magnetic nanoparticles. Well, ammonium, nitrogen and phosphorus are fairly substantial elements to all living species. However, it is that much risky as well in terms of eutrophication when considering discharge of their halogens. An adsorption method, particularly provided by iron-based magnetic nanoparticles, has a rising great attention among the other removal or recovery approaches, since its utility, simplicity in terms of design and operation, and being economic as well. Magnetite is one of the derivatives of magnetic nanoparticles, hosting various ions, molecules, and having great functional properties such as surface area, magnetism, etc. And well, the objective of this study came out of the idea behind the adsorption of the variable ammonium and phosphate ions by providing their recovery from anaerobically digested effluents. As you see in the table that shows the characteristics of various digestate effluents from different researches, these nutrients are rich in the amounts. Therefore, we've considered that the evaluation of the adsorption of these nutrients could be effective in terms of both the removal of organic and inorganic contaminants with the help of activated carbon in the composite magnetic nanoparticles form, and recovery of the ions by employing magnetic nanoparticles with bare form. And let's see very briefly the general schematic diagram of the experimental study. The experimental study involves synthesis procedures, adsorption process, separation of the adsorbents, and lastly, desorption and regeneration studies. We conducted the adsorption processes separately. We divided it into two in order to compare the adsorption performances of each adsorbent. Well, the characterization measurements were only performed for bare magnetic nanoparticles, and the regarded adsorbate was only synthetic phosphate solution. Unfortunately, due to global ongoing pandemic situation, we couldn't perform the rest of the experiments and analysis we had planned. Anyway, the characterization measurements include zeta potential, BET, SEM, and EDX analysis. Well, the synthesis of each magnetic nanoparticles was conducted with co-precipitation method. Both of the synthesis procedures are similar, And mainly the used iron salts were in a molar ratio of 2:1 in each synthesis procedure to provide magnetic nanoparticles precipitates high pH was adjusted for each synthesis procedure again. As you see in the figure 2, it shows the formation of the iron precipitates at the end of the synthesis. And at last, they were washed out and lastly left dehydrated. Well, the adsorption experiments were also conducted under batch conditions, and each one performed separately, I mean consecutively, maybe we can say. It's actually out of the simultaneous experiment. And the steps of the adsorption process is as seen on the side. These experiments carried out under batch conditions. The required amount of the magnetic nanoparticles was 0.3, and during this study, different pH conditions was performed. And after the adsorption carried out, we define the ammonium and phosphate concentration in the solution. We employed a magnet to separate the magnetic nanoparticles. At the end, the spectrophotometric measurements were carried out. And now we have the desorption processes. Well, to determine the reusability of the bare magnetic nanoparticles and the availability of phosphate recovery, desorption experiment was carried out. Flow diagram of the desorption experiment is given in the figure 4. The steps are very similar to the adsorption processes. However, the desorption of phosphorus from bare magnetite nanoparticles were carried out at room temperature with 1 hour contact time and 1 normality of sodium hydroxide solution. Now we will see the results of this study. The characterization measurements of bare magnetic nanoparticles is presented on this slide. Thanks to SEM analysis, we could obtain that bare magnetic nanoparticles were in nano sizes, and the sizes were about 50 nanometer. And the particles in the solutions are in most cases aggregates, and it is also proved by our SEM analysis actually. And the specific surface area obtained from BET analysis was about 95 grams per square meter, which is consistent with other studies present in the literature. And the zeta potential measurements indicated that the point of zero charge of bare magnetic nanoparticles was 5.6. And it is clearly understood that the magnetic nanoparticle surface charge is electropositive when the pH values are lower than 5.6, and it is electronegative at pH values higher than 5.6, and the pH value less than 5.6 would be preferred for negatively charged phosphate ions adsorption. The performances of the adsorbents and the amount of the adsorbed ions were demonstrated in the figure 7. The phosphate adsorption on bare form resulted better. Here you see in the figure 7. One of the reasons may be attributed that the activated carbon may be poorly coated with magnetite nanoparticles. So that's why the performance of composite form resulted lower compared to bare form. You can see in the figure. And moreover, another reason could be ascribed to the employment of non-oxidized surface of activated carbon. During the synthesis procedure, we couldn't modify the activated carbon surface by any agent, so that so that it may have not helped the favorable surface functional groups to be produced in activated carbon. And lastly, we had comparingly lower amount of adsorbed ammonium ions on the both bare and composite magnetic nanoparticles. This is maybe due to the acidic conditions which was conducted at the pH 3. I'm sorry. Well, we have also EDX, the result of EDX analysis. Here you see EDX analysis showed the bare magnetic nanoparticles are capable of the adsorption of phosphate ions. Here we see the effect of pH changes on the adsorption processes. Ammonium adsorption was resulted the highest at pH 3.5, but as seen, those are already close to each other. But by the way, our expectation at first was to obtain the highest adsorbed ammonium ions when the pH at 8. Ammonium adsorption on bare magnetic nanoparticles were studied by Zayer et al. Their results show that with the increase of the pH from 1 to 10, the percentage of removable ammonium ions by the adsorbent, it was increased from 20 to 90 respectively. So unlike their study, our studies, our results were close to each other. We consider that the mechanism by which the ammonia is adsorbed to the magnetic surface may be different from electrostatic attraction. More detailed studies should be conducted on this subject. And in respect to the adsorption performance of composite form, it is clearly seen our produced composite magnetic nanoparticles adsorb too low amounts of ammonium ions. Especially we've just started these ammonium composite adsorption experiments. We currently have only these results in the low concentration range, I mean, but we would like to continue these experiments at high concentration in the further experimental studies as well. On the other hand, the highest result of phosphate adsorption was obtained at the lowest pH, which was 3. With respect to this, Doe et al. Showed that the phosphate absorption by magnetite nanoparticles had a tendency to gradual decrease as pH increased from 3 to 9. Furthermore, the effect of composite form is again similarly resulted with the phosphate adsorption. Well, in the last slide, these desorption results were demonstrated in figure 11. Adsorption and desorption experiments repeated 9 times for evaluating the reusability of bare magnetic nanoparticles and recoverability of phosphate ions. And here you see in the figure 11, well, the highest desorption capacity, actually it wasn't shown in this figure. However, the desorption capacity, the highest recovery of the at the end of the desorption experiments, 94% of the recovery was conducted. The highest desorbed amount was 6.26 milligram with 520 milligram per liter in 1 hour. Thank you for listening to me. I hope you enjoyed my presentation.
Okay, thank you for your presentation. Is there a question? There is no question.
Okay.
I want to ask a question. Why did you use sodium hydroxide for desorption? Could another substance be used?
Yes, actually there are alternatives for these solutions in the literature. Just a second. Wastewater professor. Actually, oops. Okay. Oh. Sodium hydroxide solution is actually the most effective on phosphate from magnetic iron iron oxides. So this was attributed the many studies in the literature actually. So especially the study of Dow et al. I just mentioned in this slide, they actually dissolved the phosphate ions by sodium hydroxide solutions. However, this kind of experiments, I mean the desorption processes, are generally provided by the basic solutions, we can say.
Okay, based on literature.
Yeah.
Okay, thank you.
Thank you.
Yes, the next presentation will be made by Oğuzhan Şahin. Yes, Oğuzhan Şahin obtained his bachelor degree from Department of Mechanical Engineering at Ankara Yıldırım Beyazıt University. Şahin is a master's student in Department of Energy Source and Management at Çanakkale 18 Mart University. Okay, you can start presentation, please.
Thank you. Today I'm going to tell you my presentation effectiveness of fly ash in boron removal from Tuzla Çanakkale geothermal fleet. Water contamination by boron is an extensive environmental problem, since even a few parts per million present in irrigation water can cause stunting of plant growth. Referring to Nabel et al., safe concentrations of boron in irrigation water are 0.3 milligram per liter for sensitive plants, 1 between 2 milligram per liter for semi-tolerant plants, and 2 between 4 milligram per liter for tolerant plants. Therefore, extra boron in water should be removed with an appropriate method. Some areas have boron in the water in high concentration to cause boron toxicity in plants. Plants with too much boron initially display yellowing or browning of foliage. Leaf tips become dry, with the symptoms eventually taking over entire leaves. Here we can see figure 1. Several techniques have been developed for reducing boron in wastewaters, including ion exchange, adsorption, chemical precipitation, reverse osmosis, solvent extraction, and membrane filtration. Adsorption is one of the techniques which is comparatively more useful and economical. Fly ash is one of the coal combustion byproducts and the most widely used adsorbent for wastewater treatment. The potential of fly ash use in water treatment processes is obvious, as it can be obtained at low cost in large quantities. The Tuzla geothermal field, located in northwest of Turkey, is the highest temperature geothermal field in the Biga Peninsula, affected by the western extension of the North Anatolian Fault and Western Anatolia Graben systems. The Tuzla geothermal field had been an important salt production area during the time of the Ottoman Empire. In this study, boron removal from Tuzla geothermal fleet by batch adsorption method was investigated using fly ash. The effects of various parameters, such as initial pH, adsorbent dosage, contact time, temperature, were examined to determine the optimal conditions for boron removal from geothermal fluid. Fly ash was collected from the fluidized bed combustion Chan thermal power plant. Thermal power plant works 2 times 160 megawatt electric power and produces approximately 450,000 tons of ash waste per year. The characterization of fly ash was determined by BETS, SEM, EDX, XRD, and XRF analysis at the Science and Technology Application and Research Center at Çanakkale 18 Mart University. Physicochemical parameters of the Tuzla geothermal fluid were measured by using a conductivity meter. In Table 1, physicochemical parameters of the geothermal resource. A fixed amount of fly ash and 50 mm of geothermal fluid were placed in capped volumetric flask and shaken at 140 RPM using a temperature-controlled water bath with shaker for 24 hours. All the samples were filtered and the boron concentration in the supernatant was determined spectrophotometrically using Carmine method. The boron concentration of Tuzla geothermal fluid was determined as 10.3 milligram per liter. Results and discussions. Characterization of fly ash. The particle size of fly ash was between 1.45 and 186 micrometer, with surface area of 14.6 meter square per gram. The main components of the fly ash were silicium dioxide, calcium oxide, the aluminum trioxide, and ferrooxide, and the loss on ignition value was percentage of 4.7. The metal concentration contained in the fly ash was identified as aluminum greater than iron, manganese, zinc, chrome, copper, lead, cobalt, and nickel. The mineralogical composition of the fly ash comprises anhydrite, lime, hematite, cristobalite, quartz, calcite, and feldspar. Some analyses observed the ash particles had irregular morphology and micropores were found on unburned carbon. Effect of initial pH. The effect of pH on boron adsorption was investigated for different pH values. The effect of pH was investigated in the range of 2 between 12. The results were given in figure 7. That figure showed that the boron removal was affected by the pH. The maximum boron removal efficiency was obtained at pH of 4. Effect of adsorbent dosage. In order to examine the effect of adsorbent dosage on boron removal, different amounts of fly ash were added to geothermal fluid at pH of 4 and contracted in a shaking water bath at 25 Celsius for 24 hours. The removal of boron as a function of adsorbent dosage was shown in figure 8. The boron removal efficiency of the fly ash was varied approximately from percentage of 64 to 88 at the adsorbent amount of 0.25 and 2.5 gram per 50 milli, respectively. Increase in adsorbent dosage increases adsorbent surface area. The experimental data were applied to the Langmuir, Redundnik, and Dubinin-Radushkevich isotherm equations. These are isotherm equations. Another equation is Dubinin-Radushkevich. Effect of contact time. Inadequate contact time of the boron and adsorbents may not provide good removal. Therefore, optimal contact time was determined. For this purpose, geothermal fluid at pH of 4 was shaken with 2.5 gram fly ash at 25 Celsius for different periods. The results were given in figure 10. As can be seen in this figure, the boron removal was not determined until the 400 mins. Boron removal increased gradually after this period, and percentage of 88 boron removal was obtained in 24 hours. Adsorbent kinetics. In order to explain the mechanism of adsorption processes, pseudo first order, pseudo second order, and the intraparticle kinetic models were examined. Adsorption is a multi-step process involving transport of the solid molecules from the aqueous phase to the surface of the solid particulate, followed by diffusion of the solid molecules into the pore interiors. The intraparticle diffusion equation can be described as this equation. The kinetic constants were given in table 3. The results show that the adsorption kinetics of boron adsorption on fly ash in compliance with the intraparticle model, as it gives the highest R square as compared with other models. However, pseudo first order kinetics models also show a good correlation. The adsorption kinetics of fly ash was more likely to follow the pseudo first order and intraparticle models. This suggested that the adsorption kinetics of boron was controlled by the physical adsorption and diffusion mechanism that occurred at the surfaces and pores of fly ash. Effect of temperature. The adsorption of boron decreased as temperature increased, indicating that the adsorption process was favored at lower temperatures. The change in standard free energy, enthalpy, and entropy of the adsorption were calculated using the following equations. This is the ones of equation, we use them. Conclusions. In the study, fly ash, which is the solid waste product of fluidized bed combustion Chan thermal power plants, was used as an adsorbent for boron removal from geothermal fluids. This process seems economical as fly ash is available in large quantities and inexpensively. Maximum boron removal was obtained at initial pH 4 of the geothermal fluids. The results indicated that Langmuir equation is well described with the adsorption data. From the kinetic studies, the experimental results show that the adsorption of boron mostly conformed to the intraparticle model. Parameters from thermodynamic studies indicated that the adsorption of boron on the fly ash was spontaneous and exothermic process. Here is my references, and thank you for your patience and attention.
Thank you, Oğuzhan. Is there a question? No question. Oğuzhan is my master student, so I have no question too. Okay, thank you. Okay, the next presenter, Ceren Hür.
Merhaba. Hello.
Hello. Ceren studies as a master degree student at Marmara University, Environmental Engineering Department. She works as a secular in TÜBİTAK project. Okay, Ceren, we are listening to you.
Okay. I will tell you about recovery of phosphate from aqueous solution using supported engineered nanoparticles. Importance of phosphorus. Phosphorus is an essential element for all living forms, but resources are non-renewable, so recovery studies are much important. Also, removal of phosphorus in water is necessary because excess amount of phosphorus leads to eutrophication. Phosphorus is introduced to water by detergents, fertilizers, etc. Importance of nanoscale zero-variant iron. Nanotechnologies have been investigated in recent years. NZVI is the most popular because of has high active surface area due to small size in the removal of pollutants such as phosphate in water. Can remove by NZVI thanks to its active surface area. Importance of green synthesis. Meaning of green synthesis is plant extracts are used as a reducing agent for production of NZVI. Due to their antioxidant contents, for example, polyphenols. For example of plant extracts are green tea rose leaves. In this study, green tea leaves are used. Another reducing agent is sodium boride, but it has some disadvantages such as expensive, requires specific and costly equipment, produce flammable hydrogen gas, and toxic chemical. Synthesis of NZVI with plant extracts has some advantages: eco-friendly, non-hazardous, low cost, and bio-waste. Importance of clay-supported synthesis. We don't want aggregate of nanoparticles because active surface area and efficiency are reduced. Clay synthesis is provided to decrease the aggregation of nanoparticles, and bentonite is an absorbent natural cemented clay and formed by chemical decomposition or degradation of volcanic ash and lava. It is widely used in many areas such as paper, food, ceramic industry. Generally, it is non-catalytic. It has some benefits. These are low cost, large specific surface area, high cation exchange capacity, widespread availability. Ferrous sulfate heptahydrate, commercial green tea leaves, and natural bentonite are used in this study. Natural bentonite purchased from Bentash bentonite. Variables in study. The aim of study is to green synthesis clay-supported iron nanoparticles and evaluate the effectiveness of the composite material in the removal and recovery of phosphate from a synthetic wastewater streams. Synthesis variables include different clay per iron mass ratio. These are 2/2, 2/1, 2/0.56 grams, and different iron per plant extract volumetric ratio, 1/1, 1/0.5, 1/0.1. Fraction of bentonite. Bentonite was sieved to separate 3 different fractions, as can be seen on the slide. Preparation of GNZVI. 20 grams of green tea leaves and 1 liter of DI water were mixed and heated up 80 degrees and kept for 20 minutes. Then this mixture cooled and filtered. 2 grams of bentonite was added into the iron solution that include different iron masses. This mixture was stirred for 2 hours. The green tea extract was added into the solution and stirred for half hour. Different volumetric ratio are worked. The color of mixture changed to black due to formation of iron nanoparticles. The final solution was centrifuged. Composite was washed with ethanol 3 times for removal of excess amount of iron or green tea extract. After dried, and the dried composite was crushed and prepared for experiment. In batch experiment, half or 1 gram of nanocomposite, G is green synthesis, B is bentonite, and 50 milligram per liter phosphate were added into the DI and mixed it for 6 hours in orbital shaker at room temperature, and still sample was filtered and final concentration were measured by calorimetric methods. Result and discussion. Figure 1 shows removal efficiency of 3 nanocomposite that's seen in the table 1. Bentonite mass in this nanocomposite is 2 grams. Composite masses are studied between 0.1 gram and 0.5 grams. The highest removal efficiency was obtained with nanocomposite 2 at mass of 0.5 grams. Adding green tea rapidly or slowly had minor effects. Therefore, we prefer rapid addition to save time. Another figure demonstrates the result of experiment conducted with between 1.7 and 1.4 millimeter fraction of bentonite. In this set, iron masses and iron per green tea extract volumetric ratio were varied. The highest removal was achieved with 2 grams of iron at 1 per 0.5 iron extract ratio. The lowest removals were obtained when iron mass was kept at 0.56 grams. Black color has not been observed with 0.56 grams. As can be seen, iron per green tea volumetric ratio does not seem to be a significant factors in terms of phosphate removal. And last figure shows that effects of different fractions, iron masses, and constant volumetric ratio. There is not a significant difference among size fractions. It can be related with bentonite pore size. All fractions are assumed to have same pore size, so their removal efficiency are close. In terms of iron mass comparison, we achieved higher phosphate removal with 2 gram iron mass at constant iron per extract volumetric ratio. It may indicate that nanoparticle synthesis efficiency is dependent on the iron mass when reducing agent is at a proper ratio. And conclusion, green tea synthesis of nanomaterial has many advantages, such as eco-friendly, economic. Using of nanocomposite provides raw materials and energy saving, and chemical costs are reduced. Increasing removal efficiency were observed when the mass of the nanocomposite increased, and G enzyme with B can be used as a suitable adsorbent for phosphate removal. Thank you for listening. You can send your question and comments to our email addresses.
Okay, thank you. Is there a question? Okay, there is no question. Thank you very much. The last presenter, Cemre Avşar, is the presenter here.
Yes.
Cemre works as R&D specialist at Toros Agri Industry and Trade Commercial. Avşar received her BSc in Chemical Engineering from Gazi University and her MSc in Chemical Engineering in Middle East Technical University. She is still a PhD student on Chemical Engineering at Ankara University. Okay, we are listening.
Hello. Before we start, I have to say that there have been a problem with the wireless network in the office, so I had to launch via the desktop. No camera is allowed. I hope that won't be a problem. Okay. Dear listeners, I'm Cemre Avşar, a PhD student in Chemical Engineering from Ankara University and Toros Tarım R&D Center. Today, I will discuss the results of our study entitled with Evaluation of Phosphogypsum as a Secondary Resource, Effect of Acid Treatment on Purification Efficiency. But before we start, I want to give a brief information about Torostarım, which is one of the biggest inorganic fertilizer manufacturers, with the facilities located in Samsun, Mersin, and Ceyhan, producing very wide range of inorganic fertilizers and continuing to widen the family in organic fertilizer field with a facility in Gönen. Besides agricultural inputs, Torostarım also have some non-agricultural business line, such as the polypropylene and polyethylene bag manufacturing plant in Adana, which meets all of the packaging needs related with the fertilizers produced at Torostarım's own facilities, and free zone managements, provision of port terminal services, and high quality crop seedling production are the other activities of the firm. So Torostarım is a flagship company of Tekfen Agri-Industry Group, accounting around 38% of the total installed production capacity of Turkey, having the largest share in terms of installed production capacity and market share. And general products are ammonium nitrate, calcium ammonium nitrate, the ammonium phosphate, and compound fertilizers, which are NP and NPK group. And it also produces its raw materials, nitric acid, sulfuric acid, and phosphoric acid in its own plants. The first R&D center in the field of plant nutrition is established in Torostarım also. This center is continuing to cooperate with universities on projects that will support agricultural development in a sustainable manner. And this study is also conducted in collaboration with Torostarım and Ankara University. And the aim of this study is the purification of phosphogypsum from impurities by acid treatment and the investigation of the usage of purified phosphogypsum in cement and plaster industry. Here's the outline of the presentation. First, I want to emphasize the agronomic importance of phosphate-based fertilizers. Then I want to continue with phosphogypsum, its definition, chemical content, the management, and alternative recycle area is cement and plaster industry. I will continue with experimental details, give the results, discuss them, and finally conclude the presentation. Let's begin the agronomic importance of phosphate-based fertilizers. These products are effective in the plant development. Utilization of these products results increase in the grain volume and enhanced product quality. And their basic raw material is phosphoric acid, which is produced via wet process method or thermal process methods. But I will give details about wet process method. So let me continue with phosphoric acid production. So phosphogypsum is a byproduct of phosphoric acid production process, and more than 90% of phosphoric acid is produced via wet process, in which the phosphate rock is dissolved in sulfuric acid. Although wet process is economically feasible, its major disadvantage is the generation of large amounts of phosphogypsum. And according to the stoichiometry of the reaction, 5 tons of phosphogypsum is generated per ton of phosphoric acid. So the generation of the byproduct is higher than the desired product. Phosphogypsum is mainly composed of gypsum dihydrate, also containing unreacted phosphate rock and minor solid phases of reaction residues such as calcium oxide, sulfates, silicon dioxide, aluminum oxide, and fluorides. PG is also known to contain trace elements such as arsenic, silver, barium, cadmium, chromium, mercury, lead, some rare earth elements, and radionuclides. All of these impurities vary in a wide range depending on the phosphate rock used in the process, but type of the wet process, operational efficiency, age, location, or depth of the landfill also plays an important role in the properties of phosphogypsum. It is estimated that approximately 280 million tons of PG is generated annually, and it is stored as large stockpiles without any treatment, occupying considerable amounts of landfills exposed to the environment. So its management is a major problem due to large volume and large area occupation. Annual mass production of PG has promoted searching of new recycling activities. PG is mostly recycled as cement retarder, gypsum powder, or mine filling agents. And authorities worldwide are also focusing on the alternative recycle processes of PG. International Fertilizer Association, IFA, has recently published a report which gives examples of recycling areas of phosphogypsum performed by very well-known companies around the world. So let's focus on cement and plaster industry and phosphogypsum. New technologies, potential markets, and decreasing supply to natural gypsum enables an increase towards recycling processes of PG. Valorization of PG as construction material offers a promising solution since it allows continuous consumption of PG stacks. And there have been studies for utilization of PG as a substitute of natural gypsum in the production of Portland cement to control the hydration rate and retard the setting time. Also, some studies have revealed that PG can reduce the clinkerization temperature, resulting in an average 25% energy efficiency. But impurities such as alkali oxides, fluorosilicate, or heavy metals can have specific effects on clinker formation reactions according to their percentage. Chlorides, carbonides, sulfates, and phosphates have a mineralizing effect on clinker formation, and PG can be recycled as a substitute of natural gypsum, but the sulfate groups further react with tricalcium aluminate phase in the cement and resulting expansions in the concrete structure. So it is important to reduce these impurities by a considerable extent. Now I will explain the experimental procedure. So PG samples were taken from the stack and they were dried. Before washing procedure, PG was treated with 0.5 molars of sulfuric acid. And after that, experimental sets with 110 and 120 solid liquid ratio were prepared and experiments were conducted in different mixing rates. After washing with ultra-pure water, PG samples were filtered, dried, and prepared for inductively coupled plasma optical emission spectroscopy analysis via wet digestion nitric acid method. So I will give the results. Okay, from the first row, we can see that untreated PG has sulfate percentage of around 15. And the highest removal efficiency is observed in dilute solid liquid ratio, which was 1:20, and fast mixing rate. So we can see that increase in the mixing rate allows more interparticle contacts in the experimental media, resulting in an increase in sulfate removal rate. So the conclusion, we can say that phosphogypsum is the main byproduct of wet process phosphoric acid production process, and its cumulative accumulation results problems in environmental manner. Recycling and valorization of PG has gained really very attention, but its impurities makes PG unsuitable for direct utilization in various kinds of industrial. And this study focuses on the effective washing and purification of PG with sulfuric acid in terms of sulfate removal, and results indicate that increase in the dilution and mixing rates increases sulfate removal rates. And because of the protocols assigned between Torostorm, Ankara University, and TÜBİTAK, we cannot share all of the details. but this study was a brief summary of what has been done so far. Thank you for listening. If you have any questions, I will be glad to answer them.
Okay, thank you. Is there a question? Okay, there is no question.
I guess there is not. Okay.
Thank you. Yes, our session is over. I would like to thank all participants and presenters.